Hello, good evening, everyone. Welcome to today's webinar on solubility of drugs, its principles as well as applications. So before going into the topic, why the solubility is very important, especially in the pharmaceutical field. See, not only in the pharmaceutical field, even when you take in a day-to-day basis also, if some compound is not soluble in another compound, then even you cannot make your curries for eating. Suppose you're taking a salt. If it is not solubilized in the curry that you're preparing, then you cannot eat your food, isn't it? So that is a very simple example when you want to consider how important the solubility is. So the solubility is not only important in case of the pharmaceutical products, but also it is important in case of our day-to-day life. Okay, so in today's webinar, we are going to see about the following contents, like you're going to check what are the various solubility expressions in the sense how you are going to uh, say the solubility, or how you are going to define the solubility, or how you are going to designate the solubility. Also, we can consider it as a solubility expression. And then we are going to see about the mechanics, how the solubility is actually happening, what are the various components that are present in that, and what are the factors that influence the solubility, as well as the laws that govern the solubility in the formulation. So these are the various topics that we are going to discuss in today's class. So first, coming to the introduction to the solubility, first let me know what actually the solubility is. I know you may not directly able to talk to me, but you can write your answers in the chat box. I will definitely go through that, and we shall reply to your comments that you have posted in the YouTube. Thank you. So here, the solubility, what actually the solubility is, it is the maximum amount of the solute. Solute is nothing but the substance of whose solubility you want to know. So it is the maximum amount of the solute that can be dissolved in a given solvent. That is, either it could be either water or ethanol. I have just given as an example, at a specified temperature and pressure. So when you are seeing the definition here, the solute should be there, solvent should be there, and the solubility of the solute in the solvent is being governed by other two properties called as a temperature and pressure to form a homogeneous solution. So what do you mean by homogeneous solution? It is nothing but when you see a solution, it should be like a single phase. It should not have two phases. Suppose if you mix oil in water, definitely it will not get mixed. Okay. There is no solubility for oil in water. It is insoluble. Okay. So here the solubility is nothing but the maximum amount of the solute which can be dissolved in a given solvent at a specified temperature and pressure to form a homogeneous solution. So it is always essential to define the solubility clearly, because it is a foundational concept in pharmacy and drug formulation, which directly influences the drug absorption as well as bioavailability. Maybe it looks like two heavy words when I talk about the absorption, bioavailability right now at third semester. But in order to understand this in a very simple way, whenever you're taking the drug, whenever you're taking the medicine, for that, to undergo the pharmacological, to show its pharmacological action, and also to show its therapeutic action, first it should be get absorbed into the blood, because blood is the main medium through which the drug will be transported to various parts of the body. So for its solubility in the blood, again I'm telling the word we are getting, solubility. That means the solubility, as I said, you can take it as a foundational concept. So absorption is nothing but whenever you are taking any medication, its entry into the systemic circulation or blood, it is called as a absorption. Bioavailability is nothing but how much drug is available in the blood to show the pharmacological action is called as a bioavailability. So at this stage, you just need to know about what actually the absorption is and what actually bioavailability is. Right. So here for the solubility, you can simply take an example like salt in water. Okay. So whenever you are taking the salt in water, it easily gets dissolved. Why it is easily getting dissolved? because it is having ion dipole interaction, where that ion dipole interaction will be making this sodium chloride, NaCl, will be having, right? The sodium chloride is NaCl, which will dissociate into Na plus and Cl minus. So these ions will be dissolved, will be taking place in the water molecules. That is why we call it as a ion dipole interaction, and it forms a homogeneous solution. And then what is the importance of this solubility in the pharmaceutical? So we can study this importance in pharmaceuticals under two headings. The first one is its impact on the absorption and bioavailability. Just now we discussed what actually the absorption is and what actually the bioavailability is. And also the solubility of the drug in formulation and stability. So here the solubility can be considered as a major factor which affects how well the drug is absorbed into the body, especially when the drug is administered through the oral route. Okay, you must be knowing there are various routes of administration, oral, parenteral, topical, isn't it? So here, mainly for oral drug delivery, the absorption is very important. So the drug first, whenever it has been taken, it should get dissolved in the gastrointestinal fluids before it is getting absorbed into the bloodstream. So drugs whichever are having the poor solubility, they will have even lower bioavailability. Okay. For example, I can take this as the students who are regular to the college will understand what actually is happening in the class. And students who are not regular, they cannot understand what is happening in the class. They may study well, they may read the textbooks, or they may take some lecture notes, and they may prepare for the exams. But what actually is happening in the class will be known by the students who are present in the class, right? So here students who are present in the class, it is called as a solubility, and understanding what happening in the class is called as a bioavailability. Both are interrelated. So whenever the solubility is less, obviously the bioavailability will also be less. This is how you can remember here what is the influence of solubility on the bioavailability. For example, you can take the drugs like ibuprofen, griseofulvin. They have low solubility. So when their solubility is low, what happens to the bioavailability? Obviously, there will be reduction in the bioavailability. So now, in order to prepare such dosage forms for such drugs, you have to go for certain mechanisms which improve their solubility, simultaneously improving the bioavailability. That is how the solubility is important in absorption as well as the bioavailability. So the second one that we have is the solubility in drug formulation as well as the stability. So the solubility of a drug generally determines which type of formulation can be used, whether they can be prepared as a tablets or whether they can be prepared as a injections or topical dosage forms. You can decide the type of the dosage form depending upon the solubility of your drug. So highly soluble drugs can be prepared as a simple solutions, whereas poorly soluble drugs may require certain techniques to enhance their solubility. Like there are various techniques like solid dispersions, nanoparticles, emulsions. Like that, we have various techniques which are used to enhance the solubility of the drug. And then how this applicable, like applications of the solubility in drug delivery systems. So the solubility plays a major role in three of the drug delivery systems. One is oral drug delivery system, then injectable solutions, and then third one we have is a topical and transdermal drug delivery system. As I already said, oral drug delivery, before the drug is getting absorbed into the bloodstream, it has to get dissolved in the GI fluids. Okay, so when it is getting dissolved in the GI fluids, if it is not having a proper solubility, then it cannot be absorbed properly, right? So then injectable solutions for the parenteral drug delivery, if the drugs are not completely dissolved in the given given solvent, then what happens? You cannot inject that to the body because they will be present as a solid particles, which will even lead to the fatality of the patient. That means it may lead to the death of the patient as it obstructs the blood flow, right? And at the same time, for the topical and transdermal are nothing but which we apply on the skin, right? So when we are applying on the skin, they should have perfect solubility with that of or perfect absorption into the skin when you are applying on the skin. If the absorption is not proper, if the solubility is not proper, then it cannot be absorbed properly into the skin. Okay. So from this slide, you must have understood how important the solubility is in determining its absorption, bioavailability, as well as making the formulation choice. Okay. So depending upon the solubility, you can even decide which type of the dosage form you can prepare for your drug, and also what is its effectiveness in the drug delivery. That is why we say that the solubility is very, very, very important when such like during the formulation of any pharmaceutical dosage forms. Next, coming to the solubility expression. So you know well what an expression is. If you are serious, your expression will be different. If you are very happy, your expression will be different. If you're sad, your expression will be different, isn't it? So in the same way, depending upon what type of the solubility it is having, the expression would differ. So how we are representing a particular solubility, it is called as a solubility expression. So this can be expressed in various ways to quantify how much solute can dissolve in a solvent in specific conditions. So these solubility expressions are mainly useful in order to say how much amount of the solute can be solubilized in the solvent. And we have two types of expressions, solubility expressions here. One is qualitative expression and the another one is a quantitative expression. So qualitative in the sense you can just say whether it is soluble or not. Okay. So qualitative in the sense when I see you, I can just say whether you're, for example, by seeing you, I can just say, yes, she is very clever. But I doesn't know unless and until if I see your marks, whether you're clever or not. Of course, marks are not the indication of the talent or something, whatever the proverbs that we have, we can use that. But however, the qualitative terms are different from that of the quantitative terms. So qualitative solubility expressions, these are usually described in relative terms based on the amount of solvent required to dissolve a given amount of a solute. So how they are expressed, either very soluble, freely soluble, sparingly soluble, slightly soluble, very slightly soluble, partially insoluble, like this. We have the qualitative terms. Here, by seeing this, you cannot say that how many grams of your solute is soluble in how many liters of your solvent, because this is only qualitative. And then the next one we have is the quantitative solubility expressions. That is the molar solubility, percentage solubility, weight in weight. Okay, weight in weight. That is the first one, numerator one designates the amount of solute, whereas the denominator one, it designates the amount of solvent. So weight in weight, weight in volume, volume in volume, and miscibility. Miscibility here is nothing but the miscibility is different from that of the solubility. Solubility means it is completely solubilized in the solvent, whereas miscibility is it is not completely soluble. However, because of the influence or because of the interaction of certain agents, one component is miscible with the other component. That is the difference between solubility and the miscibility. So this is how you can express the solubility either qualitatively or quantitatively. So yes, madam, you have been keep on telling about solubility, 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 how actually this solubility happens. That means in order to know how this solubility is actually happening, we have to know certain interactions that occur between the solute and the solvent. Because you know that in a solubility, to determine, to express a solubility, you need two components. That is a solute as well as a solvent. So now let us see what is the mechanism of the solute solvent interaction. So any interaction that happens between a solute and a solvent, it leads to the homogeneous solution. And the nature and the strength of these interactions, it will determine the solubility. Okay, so the nature and even the intensity of these interactions, they will determine what is the extent of the solubility. So what we will get by understanding all these interactions? When we understand these interactions, it helps in predicting the solubility of drugs and designing the suitable formulations. At the same time, these mechanisms are they vary based upon the polarity, structure, as well as the properties of both the solute as well as the solvent. So now we'll see what are these various interactions. So we have four types of the interactions. ionic solvation, hydrogen bonding, dipole-dipole interactions, and van der Waals forces. We will see one after the other. So this ionic solvation, it occurs when an ionic compound dissolves in a polar solvent. So in water, for example, partial charges of the water molecules interacts with the cations. What are the cations? The positive ions are the cations and negative ions are the anions. So they break the ionic bond and then help in solvating the ions. Again, we can take the same example of NaCl, that is sodium chloride. They are going to form as the Na plus and Cl minus. So here, these are the cations and these are the anions that are present, and they break the ionic bonds and help in the solvation of the solutes. And then the second one that we have is the hydrogen bonding. So this hydrogen bonding, it involves the attraction between a hydrogen atom bonded to a electronegative atom. So electronegative atom examples, oxygen or nitrogen, okay, and another electronegative atom. So in this way, the hydrogen bonds increase the solubility of polar molecules, as these hydrogen bonds are relatively strong, and also they stabilize the solute molecules in the solvent. Here you can take the example as ethanol in water. This ethanol, which group will be present in ethanol? It is a hydroxyl group, that is OH group. So the OH group in this ethanol, it forms a hydrogen bond with the water, making this ethanol getting solubilized in the water. This is how the hydrogen bonds help in solubilizing. And then dipole-dipole interactions. The third one that we have is the dipole-dipole interactions. So this occurs between the molecules with permanent dipoles, such as polar organic compounds and polar solvents. Here, the positive end of one polar molecule, it will attract the negative end of the another, so that they are stabilizing them in the solution. So here you can take the example as acetone in water. The polar carbonyl group that is present in the acetone, it will interact with the water molecules through dipole-dipole interaction, and it makes the acetone miscible in water. Okay. And then van der Waals forces, the last type of the solute solvent interaction that we have is the van der Waals forces. These are also called as a dispersion forces. Van der Waals forces, these are also called as a dispersion forces. These are weak nonpolar interactions which occur between the molecules with a temporary dipole, mainly in the nonpolar solvents and the solutes. So these temporary dipole molecules, they will be attract to each other. The attraction will be very weak, which is enabling the solubility in the nonpolar solvents. Here the example is oil in hexane. The nonpolar molecules in both oil as well as hexane, they interact via the van der Waals forces, which is allowing them to get mixed up. Okay, so this is how the solute and solvent interactions happen with the various types of the interactions. 4 types: ionic, hydrogen, dipole-dipole, as well as the dispersion forces. Right. So with these forces, the solubility is happening. What is the actual mechanism of the dissolution in the solvent phase? Okay. So the next one that we have, mechanism of dissolution in the solvent phases. Here we have 3 steps. Okay. The 3 steps that are involved in the dissolution in solvent phases is solute molecule separation, solvent molecule separation, and solute solvent interaction. So for example, let me show here. These are the solute molecules that we have, which should get dissolved in the solvent. Okay. So when this solute molecule has to come and dissolve in the solvent, first the solute molecules should undergo separation. That means there should be spaces present between the solute molecules, and then the solvent molecules, they should create some spaces among them so that they can accommodate these solute molecules in the solvent. Now the accommodation should happen like this. So the solute molecules have accommodated, which finally leading to the solution. That is, the solute will get dissolved in that of the solvent molecules. So the solute molecule separation here, They must overcome the intermolecular forces that are present between the molecules of the solute, and they should separate from each other. So this process, it requires certain energy, right? Suppose you're a group of 6 people, we want to separate you. We need some energy to separate you, isn't it? So that is how the solute molecules also need energy to get separated from each other. And solvent molecule separation here is the solvent molecules, they have to create space among themselves, and this also requires a energy. Now, when the solute solvent interaction is happening, the solute molecules will be interacting with that of the solvent molecules, which releases energy. It is not requiring energy here, it is releasing energy. So this step is the actual step which is helping in the dissolution, especially if the energy released in the third step is greater than the energy required in the first and the second step. Okay, so this is how the dissolution happens in the solvent phase. That is what we have given the example here regarding the sodium chloride in water. And then what are the various factors that affect the solute solvent interactions? The first factor, it is the polarity. Okay, you must have listened so far, like dissolves like. Okay, polar solutes will be solubilized in the polar solvents. Non-polar solutes will be solubilized in the non-polar solvents. Okay, so and then the next one is the temperature, right? Even you must have seen at your home, whenever your mother wants to prepare the gulab jam, she will be dissolving the sugar in water, but at some time the sugar will not get dissolved in water. Okay, because it has become saturated. We have 3 types of the solution: saturated, unsaturated, and supersaturated. So when your solution becomes saturated, you have to give certain energy from the external so that the solute will get dissolved in the solvent. What is that energy that your mother gives? She will put it on the stove and she will heat the water. So whenever the water is being heated, the solute will undergo the solubility enough, and then it will get solubilized in the water. So here, higher temperatures, they will increase the molecular motion so that they enhance the solute solvent interactions and also the solubility of the solids. However, the reverse happens in case of the gases, because the gas solubility in liquids, they decrease with increase in the temperature. And then next property that we have is the pressure. So pressure, it mainly affects the gases. Higher pressure, it increases the gases solubility in liquids because of their closer molecular interactions. For example, very good example I can give you here: carbonated drinks, all the cool drinks. Okay, so all the cool drinks, whenever you have taken, when you just pour them out, they will give the bubbling. Why are they giving the bubbling here? Because the carbon dioxide that is present in the cool drink, it is more soluble under high pressure. Okay, it is more soluble under high pressure. When you're opening the ductine of that, the cap of that bottle, what is happening? The pressure is released. So when the pressure is released, the effervescence will come out because it is soluble only under higher pressure. So as long as the cap is fixed on the bottle, it is not showing any effervescence. Once the cap is removed and you can see that effervescence out of the, right? So in this way, these are the 3 major factors which are going to influence the solubility. So why these solute-solvent interactions are important in the formulation? Again, so far we discussed, it is going to influence the drug bioavailability, formulation development, as well as stability and the storage. So now you must have understood by all these 4 to 5 slides, you must have understood what are the various solute-solvent interactions that are affecting the drug solubility, and also how they are influencing the formulation definitions, right? Formulation decisions. And then next we are going to see what are the various factors that are influencing the solubility. We have seen the 3 factors like polarity, temperature, and the pressure. Now, based on that, we are going to see a few more factors which are affecting the solubility. Because the solubility, it always depends upon the physical and chemical factors. So now understanding these factors will help any person who are going to optimize the formulation for their effective drug delivery. So the first and foremost thing is the temperature again. So for most of the solid solutes, the solubility will be increased with increasing in the temperature. So whenever there is reduction in the solubility, immediately you have to give some external energy to that in the form of a heat or temperature, so that the solubility of a solid can be enhanced. And then again, second one we have is the pressure. We have seen in detail about pressure by taking the carbonated drinks. So this pressure, influence of pressure will be said by Henry's law of gases. Okay, this law is going to govern how pressure is influencing the solubility of gases and liquids. And then the next one we have is the nature of solvent and solute. Again, in the polarity, I said that like dissolves like. So polar solvents dissolve the polar or ionic compounds due to electrostatic interactions, hydrogen bonding, as well as the dipole-dipole forces. Whereas non-polar solvents will be dissolving the non-polar solute through van der Waals forces. So the solute and the solvent polarity, it will determine how the solvent is going to solubilize the solute. For example, take vitamin C. Vitamin C, it is polar in nature. It is water soluble, but it is not oil soluble. At the same time, vitamin D, it is a non-polar one, which dissolves in the oil, but it cannot be dissolved in the water. That is why we say like dissolves like. And then the next one we have is the pH and ionization. So the solubility of ionizable compounds, it always depends upon the pH of the surrounding environment, as it affects the ionization state of the solute. For example, weak acids, they are more soluble in the basic conditions. Basic conditions in the sense alkaline pH, higher pH. Whereas weak bases, they are more soluble in the acidic conditions, that is lower pH. You know, there is a pH from 1 to 14, 1 to 7 they are acidic, 7 to 14, 8 to 14 they are alkaline, 7 is a neutral one, right? So the pH adjustments can be made so that if any solubility problem is there, it can be covered. For example, aspirin. Aspirin, it is more soluble in the basic pH of the intestine than the acidic pH of the stomach. So by adjusting the pH, formulations can target in the GI tract where the drug dissolves and they get absorbed. And then the next property that we have is the particle size and surface area. Okay, so the particle size is nothing but, for example, take a chalk. Okay, the chalk piece. Whatever the chalk that you have, if you just place it, say this is a chalk, I have placed it on the table. So when I placed it on the table, the surface area that has been occupied by this chalk, only this rectangle. Is it not? Now I have made the chalk into powder and now I have dispersed. I have just kept it on the table. Now what is happening? It has been spread over all. Has been spread overall, and then it is covering the surface area more than the actual chalk. That means reduction in the particle size, it is going to enhance the surface area. So when the surface area is enhanced, the rate of the dissolution as well as the solubility also increases. That is why in order to reduce the size of the particle, we have various mechanisms like micronization, nanonization. Like that, reduction in the particle size will improve the surface area, which eventually improves the solubility as well as the bioavailability. And then the next one that we have is the co-solvent system. So the co-solvents are nothing but the secondary solvents which are used to increase the solubility of poorly soluble compounds by altering the solvent environment. So the common co-solvents which we use are ethanol, propylene glycol, glycerin. Okay, generally these are used to dissolve the hydrophobic drugs in the water. Hydrophobic are water hating, hydrophilic are water loving. Okay, so these co-solvents, they modify the polarity of the primary solvent and they make the environment more favorable for the dissolution of the solvent. And then the next one that we have is the presence of surfactants. So here the surfactants means they reduce the surface tension and help in the solubilization by forming a micelles around the non-polar drug molecules. It may be like quite a bit tough for you to understand to about The surfactants, they consist of a hydrophilic head. These are the hydrophilic head, and these are the lipophilic tails. That means we call them as the amphoteric compounds because they are having both hydrophilicity as well as the lipophilicity. So when we use the surfactants, they form the micelle. Micelle is nothing but just like a cluster. In this way, it is going to form the cluster, and then it gets slowly dissolved in the solvent that you have taken. In this way, the surfactants are going to reduce the surface tension of the compound and helps in the solubility of the drug. And then the last one that we have is the complexation and salt formation. So some of the drugs, they form complexes with the other molecules. You can take the example as a cyclodextrins. So cyclodextrins are those which form the complexes to enhance the solubility and also converting the drug into their salt form, either sodium form or hydrochloride salts. They improve the solubility by enhancing the ionization. And also the complex and salts, they are widely used in order to enhance the solubility as well as stability in various dosage forms. Okay, so now all these are some 7 to 8 factors which are going to affect the solubility of any drug in the solvent system. Hope you have understood and hope you have uh, been thorough with how these factors are influencing the solubility. Then, coming to the solubility loss. Okay, so not LOS loss, it is LAWS loss here. So the solubility loss, what is the purpose of this solubility loss is, we have two solubility laws, Rawls law and distribution law. So this Rawls law and distribution law, they will help to predict how substances will be behaving in the mixture, which is always essential for designing and optimizing the drug formulations. At the same time, what is the importance of these laws in the pharmaceuticals? These laws, they help in understanding the solute behavior in the solutions, mixtures, as well as the different phases, so that it will give some idea on which type of the dosage form or drug release and bioavailability will be there for your particular dosage form. Okay. So now first let us dwell into the Rawls law. What actually the Rawls law is. So this Rawls law, it describes the vapor pressure of an ideal solution and states that the partial vapor pressure of each component in a solution is directly proportional with mole fraction. This is what the definition of the Rawls law is. Okay, and Rawls law is always applicable to the ideal solutions, but not for the real solutions. So now, in order to understand this particular Rawls law, we have to see what is the derivation. Okay, how this Rawls law has been explained by using the derivation. So, as I said, the Rawls law states that the vapor pressure of an ideal solution is directly proportional to the mole fraction of the solvent present in the solution. So, mathematically, it can be written as PA is equal to PA naught multiplied by XA. So, what are this PA, XA? So, PA is nothing but vapor pressure of the solvent in solution, and then PA naught is vapor pressure of pure solvent, and XA is mole fraction of pure solvent. So this is the equation. So for example, in order to know about the derivation, if you consider an ideal solution where a non-volatile solute is dissolved in a volatile solvent, for an ideal solution, there are no changes in the interactions between the molecules. That is, solvent-solvent, solute-solute, and solute-solvent interactions, everything will be equal. So here, let us consider Na and Nb as the number of moles of the solute and solvent and solute respectively. So you can write its mole fraction as XA is equal to Na by Na plus N. If you want to write the mole fraction of component B, then you can write it as XB is equal to NB by NA plus N, right? So in a pure state, the vapor pressure of the solvent is always PA naught. And when the solute is added, the number of solvent molecules at the surface of the solution decreases, leading to the reduction in the vapor pressure. So now, according to the Raoult's law, the vapor pressure PA of the solvent in the solution, it is proportional to the mole fraction. So PA is equal to PA PA naught into XA. If you want to write it for PB, it is PB naught into X. This is how you can write the derivation of the Raoult's law. So this Raoult's law, it shows that the presence of a solute, it will lower the vapor pressure of the solvent due to decrease in the number of solvent molecules that are escaping into the vapor phase. Okay. So this is what we have seen. And the most important applications that we have here is it is fundamental in designing the solutions where vapor pressure control is necessary, like transdermal patches or inhalable drugs. In such cases, you need to know what is the vapor pressure of each of the molecule. And it is also used in calculating the boiling as well as freezing points of the drug molecule. And then the next one that we have is the distribution law. Okay. So this distribution law, it describes how a solute distributes itself between the immiscible solvents at equilibrium. Why we should know about the immiscible solvents and about its distribution in the immiscible? I'll tell you. In our body, the blood is considered as an aqueous phase, water phase. Okay. If the drug has to enter into the blood, it has to cross various membranes. Those membranes are lipophilic in nature, which we consider them as an organic phase. Okay. So if your drug is not able to solubilize or not able to get distributed into the aqueous phase, then it will be difficult for your drug to enter into the bloodstream. Hope you are getting my point. Okay. So if your drug is not having the distribution into the water phase, then it will be always difficult for it to move into the bloodstream. And the reverse happens when the drug is having more solubility. It cannot cross the membrane because it is hydrophilic in nature. That is why we should know about the distribution law. And this distribution law is also called as a partition law. So now let us see what is the derivation for that. For example, if a solute S is there and it is distributed between two immiscible liquids, say A and B. Okay, so then at equilibrium, the ratio of the concentrations of solution in the ratio of concentrations of the solute in each solvent will be constant. So Ca divided by Cb will be equal to K. So what is the Ca and Cb? The Ca is concentration of the solute in solvent A and then concentration of solute in solvent B. And K is called as a distribution or partition coefficient, which is constant at a given temperature. So now if you are considering a solute S is distributed between the two immiscible solvents A and B under equilibrium conditions, the solution will take, like according to the law of chemical potential equilibrium, the activity of the solute in both phases must be equal. So activity of A must be equal to activity of B, where this alpha A or alpha B, they represent the activities of the solute in both the solvents A and B. Whereas for dilute solutions, the activities can be replaced by the concentration. So this is replaced by Ca by C equal to. In this way, we got the equation as Ca by Cb is equal to K. So in this way, when we are deriving the equation for this distribution law, we should also know what is its application in the drug formulation, right? So this distribution law is very much critical for predicting the drug's absorption, permeation, and as well as the bioavailability, because these factors will influence the formulation choices, whether you have to go for oral, or topical or even the injectable routes. So this is how the Rawls law as well as the distribution law, it is going to govern how or which type of the dosage form that you have to prepare and how it is finally affecting the therapeutic efficacy of your drug. Hope you're following me. So going to the next topic, what actually, we have to see Rawls law versus distribution law. So this Rawls law, first let us see what actually the significance of this study is. So Rawls law, it is used to determine the vapor pressure changes, which is valuable in formulations involving the volatile solvents. Okay, so it is going to tell about what are the vapor changes. Sorry, vapor pressure changes. And here distribution law, it is going to tell about drug permeability and absorption, which is essential to determine in which route of administration you have to give your drug. And also the Rawls law, it helps in predicting the boiling point elevation as well as freezing point depression so that you can know at what temperature or pressure you can store your liquid dosage forms. At the same time, the distribution law, it is going to guide the design of emulsions, micelles, as well as the liposomes, where drugs need to distribute between the lipid as well as the aqueous environment. Let me give you an example here. For example, a topical cream will be there, which you apply for the skin. It will be consisting of both hydrophilic as well as the lipophilic phases. So the distribution law will help you to understand how you can achieve the optimal drug distribution and drug release by calculating what is the partition coefficient of the drug between the cream's lipid as well as the aqueous phases. This way, the distribution law will be used in determining the activity of any topical dosage. And then what are the limitations? We have certain limitations to the laws. So here in the Rawls law, as I said in the beginning, these are applicable only for the ideal solutions, but not for the real solutions. Okay, because here the intermolecular forces between the solute and solvent are similar, which is rare in case of the complex drug molecules. Whereas non-ideal solutions, they may not stick or they may not obey the Rawls law, so that the adjustments have to be done. Coming to the distribution law, here the partition coefficient only applies under standard condition and they do not affect for metabolism or protein binding or even other physiological processes which influence the solubility inside the body. So the real world drug absorption and distribution, it may deviate from the predictions as biological environments are complex as well as multi-phased. So it is just a prediction. However, it is not correct when we are actually going into the sea. Okay. So here you should understand that the Rawls law will always help in controlling the vapor pressure in pharmaceutical solutions, and also how the distribution law is helping in predicting the drug distribution between the. These principles mainly guide the formulation decisions, which allows the scientists to both control the solubility as well as drug behavior across the formulations. And then what is the importance of solubility in drug formulations? Okay, so as we said that the solubility is the most important property in the drug formulation, because a drug should be soluble in order to get absorbed, then reach the therapeutic levels, and then deliver its pharmacological action and give the output. But what are the various challenges or what are the various disadvantages that we face because of this solubility? Mostly 40 to 50% of the new drug molecules, whichever we are inventing, they have very poor water solubility. So that for that reason, we should know what are the various formulation strategies that are present in order to enhance the solubility of any drug molecule. Okay. So the first one is solubility in the drug formulations. Why we need to know about the solubility? As I said, as it is governing the absorption as well as the bioavailability, the solubility has to be known. And then solubility and bioavailability. So bioavailability, now as you have got some information about the absorption and bioavailability, now you can go for next grade of definition. Like it refers to the proportion of a drug that reaches the systemic circulation and is available to act on the target sites. So solubility is always a primary factor which affects the dissolution rate and consequently the bioavailability of the drug. Whereas poorly soluble drugs, they dissolve slowly, where they limit the amount available for the absorption, resulting in the lower bioavailability. Okay. And then solubility in different drug delivery routes. The first slide itself we discussed. Oral drug delivery is a major route of drug delivery where solubility plays a major role, followed by the injectable formulations, then topical formulations. Okay. And then solubility and stability in the formulations. So here, the solubility, it is going to affect the chemical as well as the physical stability of the drug. And the drugs which are not fully dissolved, they may get precipitated or even they undergo degradation, which is affecting the shelf life of the product. So always the solution, syrups, injections, which which require the drug to remain in the solution all through the shelf life of the product. The insoluble drugs, they may undergo precipitation or they may undergo sedimentation and they may show some instability problem. And role of solubility in drug release and therapeutic efficacy. Because as I said, they are influencing the absorption as well as the bioavailability. If the solubility is less, the dissolution time will be more. If the dissolution time is more, the bioavailability will be less. When all these are less, the therapeutic efficacy comes down. In order to show the therapeutic efficacy in half an hour, it may take up to 50 minutes to 60 minutes. For example, I'm telling you, in order to show the therapeutic efficacy of any drug, right? And then finally, we have solubility enhancement techniques. So solubility enhancement techniques are nothing but here. When you know a particular drug is having a solubility problem, you should also know how you can rectify that solubility problem. Okay. Now it is too early for you to know about various methods that are used to enhance the solubility, because in future semesters you will be learning about that. Just now in the earlier slides we discussed about the particle size reduction. Okay, reduction in the particle size as it is going to enhance the surface area. And we have seen surfactants can be used, co-solvents can be used. Like this, there are various methods. Almost by the time when you come to the 6th semester and read about BPPK, this itself, it deserves 2 or 3 classes where we have at least 15 to 18 methods which are used to enhance the solubility of the drug, so that eventually the bioavailability will be enhanced. So this is all about today's topic. We have discussed about what actually the solubility is and what are all the solubility expressions that we have, and how the solubility can be expressed both qualitatively as well as quantitatively. And also we have seen what are the various factors affecting them. Very important one that we have seen is the solute-solvent interactions, and also how this solute is getting dissolved in that of the solvent, right? And then we have seen about the 2 important laws, Rawls law and the distribution law. Hope you have understood, because this solubility, it is very important for you to know about the solubility, as it is a primary property which decides the everything in future about the drug. Okay, everything in future about the drug will be decided by this single property. So that is why it is very essential to know about the solubility and its properties. So I hope everyone have understood this topic. If you have any doubts regarding the topic, please post your questions in the chat box. We will get back to you very shortly with the answers. Thank you so much for attending the webinar. See you all in the next webinar.